The Chevrolet Corvette ZR-1, a showcase for technological superiority that maintains Corvette's tradition of performance leadership it's enjoyed for over 3 decades. Now, since the 1990 model year introduction of the ZR-1, Corvette's reputation has been elevated to the highest levels as it competes tire to tire with the world's most exotic production sports cars. Perhaps the ZR-1's most remarkable trait is its unique split personality. Here, in one package, is a car capable of truly spectacular levels of performance while still meeting or exceeding every government standard for fuel economy, safety, noise, and emissions. It's even capable of running on regular grade fuel. The ZR-1 is able to accelerate from 0 to 60 in about 4.2 seconds. It can run a quarter mile in under 13 seconds, crossing the traps at 114 miles per hour. Contributing to the ZR-1's superb traction and control capabilities are the widest ever unidirectional Goodyears ever fitted to a Corvette. Added to that is one of the most sophisticated anti-lock brake systems available on a production automobile. In 1992, this system was augmented with a traction control function which increased the incredible capabilities of the ZR-1 to even greater heights. Standard on ZR-1 is the Z51 Performance Handling Package, which includes heavy-duty front and rear springs and stabilizer bars, heavy-duty 4-wheel disc brakes, and a power steering cooler. Also standard is the sophisticated speed variable suspension FX3 selective ride control system, which allows the driver to choose via a cockpit switch from performance, sport, or touring modes. Each of these modes has 6 different shock absorber damping levels determined by vehicle speed. As the ZR-1 speed increases, the suspension is automatically firmed up. Small external electric motors controlled by the ride control module turn internal rotary valves in each shock absorber to modify damping as required. This system was jointly designed by GM Engineering and the noted suspension experts at Bilstein Engineering. Similar systems are currently found on the Porsche 969 and Lotus Formula One racing cars. The combined result is a car capable of braking and cornering power in excess of 1 G. In case you're wondering, the name ZR-1 is not an entirely new designation for Corvette. From 1970 to 1973, the name was used to describe an option package used for racing. It included a 330 horsepower, 350 cubic inch V8. Records show that a total of 53 ZR-1s were produced. One of the ways today's ZR-1 achieves its dual personality is the 6-speed manual transmission designed by ZF, the respected German gearbox builder. Rated at 425 pounds-feet, it incorporates a computer-aided gear selection system that guides the driver from first to fourth gear during light throttle driving. Second and third gears are engaged only when the driver requires the ZR-1's highest levels of performance. Although differentiating a ZR-1 from an L98 model takes a discriminating eye, this power key is a sure indicator that this is no standard Corvette. In normal, the ZR-1's enormous capabilities are kept in harness, with power limited to just below that of an L98. Only when the switch is turned to full is the awesome capacity of the ZR-1 unleashed.
End Part 1. You should now prepare to take the first part of the test for this course. To take the test, you must have a number 2 pencil and the official student attendance and test form in front of you. Make sure the first 7 digits of the course number printed in block 9 of the student attendance and test form match the first 7 digits of the course number printed on the course book and the videotape label. If you do not have the correct materials, stop the video and get them. Begin by placing the student attendance and test form in front of you so that the clipped corner is in the lower right. In the upper left-hand corner of the form, you will see a series of circles below the letters A through E. At this time, you will be filling in the test answers only. At the end of this video, instructions for completing the remainder of the form will be provided. This is the only answer sheet you will need for this course. In a moment, you will see the first test question and several possible answers. When you have decided on your answer, completely fill in the circle below the letter corresponding to the correct answer. Since this test will be corrected by computer, it is important that you avoid making stray marks on the paper. If you change your mind about an answer, be sure to erase your first choice completely before marking the correct answer. It is also important to avoid getting dirt or grease on the answer sheet, or folding it, as this may cause the computer to incorrectly score your test. As you take this test, remember that there is no time limit. You may take as much time as you wish to complete the test. You may also review the course book or rewind the videotape to find the correct answer. Begin Test Part 1 at line 1 of the test form. Test Part 1. Question number 1. The standard RPO performance handling package on a Corvette ZR-1 is A. Z25, B. Z51, C. Z61, or D. Z87. Question number 2. The standard RPO selective ride control package on a Corvette ZR-1 is A. FE3, B. F41, C. FX3, or D. FW1. Question number 3. The company which manufactures the 6-speed transmission that is standard on a Corvette ZR-1 is A. ZF, B. Borg-Warner, C. Muncie, or D. Hydromatic.
At the heart of the ZR-1 is an all-new V8 designed specifically to make this the fastest production car in the world. Horsepower is rated at approximately 375 at 5,800 RPM. Torque is about 370 pounds-feet at 4,800 RPM, or about 30 more than a standard L98. Redline is set at 7,072 RPM. The LT5 weighs about 39 pounds more than an L98 due to additional weight in components such as the camshafts, connecting rods, cylinder heads, exhaust manifolds, crankshaft saddle, injector housings, and cylinder liners. Its 12-quart oil capacity, 7 more than a standard Corvette, adds to its weight. In total, a ZR-1 weighs about 140 pounds more than a standard L98 Corvette equipped with manual transmission. To say that the LT5 is completely new is not totally accurate. It shares the same rear main bearing seal with the L98 power plant. The LT5 is the result of a joint engineering effort between General Motors Chevrolet Pontiac GM of Canada, or CPC Group, and Chevrolet Motor Division, which actively participated in the design process. GM's Group Lotus Engineering Center in Hethel, England, added its skills and expertise in the area of dual overhead cam racing engine technology. Lotus was responsible for the total design, release, and validation of the engine. And Mercury Marine in Stillwater, Oklahoma, was tapped to manufacture the engine. With many years' experience of working with limited production small block Chevrolet engines, Mercury Marine individually hand-assembles each LT5 in a special clean room environment. All reciprocating parts are assembled in matched sets, enabling the engines to meet a final balance specification of 1/2 inch ounce, or about a third of what the most perceptive driver can feel. Before shipment, each engine is hot tested for nearly an hour. Featuring numerous new designs, the LT5 reflects much of its traditional Corvette heritage. Displacement, like millions of other small block Chevrolet engines, is the same 5.7 liters or 350 cubic inches. Cylinder bore spacing on the LT5 remains at 4.4 inches, although the bore has been reduced from 4 inches to 3.9 inches. And the stroke has been increased from the L98's 3.48 inches to 3.66 inches. A Delco-Remy Nippondenso gear reduction starter is located beneath the ignition module, contributing to the narrow overall width of the engine. The LT5's all-aluminum cylinder block is constructed in the cast-in sand method. Deck height is 9.03 inches. Its wet sleeve open deck design features Nicosil-plated aluminum liners that are seated on a shoulder, which forms the bottom of the block's water jacket. A patented Nicosil coating process permits very close tolerances necessary for good production and long-term durability. As an added benefit, the Nicosil saves weight and promotes ring sealing. A 1 millimeter flame guard lip at the top of the liner protects the head gasket. The block is split at the crank center line. The aluminum crankcase includes cast-in-place nodular iron main bearing caps. It is bolted to the cylinder case in order to create a rigid support for the crankshaft. External ribs cast into the cylinder case further increase strength. The LT5's head has 4 valves per cylinder. An included angle of just 22 degrees keeps the head narrow enough so that the standard Corvette frame rails didn't have to be revised for production. 4 overhead camshafts are employed with direct-acting hydraulic lifters. This design eliminates the need for supplemental adjusting fingers, rockers, or other mechanical linkages that add unnecessary weight. A 16-runner intake manifold brings plenty of fresh air to the cylinders. And 2 Multec fuel injectors per cylinder, plus a unique secondary inlet port throttling system, make this LT5 unlike any other production engine ever built by GM. In order to accommodate this unique induction system, inlet valves have distinct primary and secondary designs to mate with the cam contours on each inlet camshaft. Secondary cam lobes have a 20-degree greater duration period, which increases high-speed power. The camshafts are driven by a small block type primary chain that drives an idler located in front of a roller chain sprocket on a common hub. The LT5 head is a cloverleaf design which incorporates centrally located spark plugs for optimum volumetric efficiency. By placing the spark plug in the middle of the valves, the distance the flame travels is reduced. Each lip of the cloverleaf forms a small quench area which directs the air-fuel mixture up toward the spark plug while generating turbulence in the cylinder. The unusual design of the head permits the compression ratio to reach 11:1. The flat area around the perimeter of the mildly dished aluminum pistons works in conjunction with the cloverleaf head design to control combustion. This design permits the use of 87-octane unleaded fuel if the higher minimum recommended 91-octane fuel is unavailable. Although the LT5's induction system appears similar to the L98's tuned port injection system, there are significant differences. The throttle body, for example, has 3 butterfly valves rather than 2. There is a very small 22-millimeter diameter primary valve that is used for low-speed drivability. Then there are 2 larger 59-millimeter diameter secondary throttle blades that open beginning when the primaries are 80% open and are completely open at full throttle. The LT5's electronically controlled sequentially fired fuel injectors are targeted over each intake valve. This configuration releases fuel into the combustion chamber once per cylinder firing stroke, unlike the L98 simultaneous double fire system that releases fuel each time the piston moves up in the cylinder. The intake ports, as well as the valves, cam lobes, and fuel injectors, are divided into primary and secondary groups. The primaries are the ones toward the front of the engine. The secondary ports are about 5 to 10% larger in diameter and contain a port throttle butterfly that is actuated through a mechanical linkage by a vacuum diaphragm controlled by the ECM. With the engine power switch on normal, the engine runs on 3 valves per cylinder. The secondary intake valve is moving, but because the butterfly valve is closed, the fourth valve is essentially non-functional. However, with the engine power switch on full, and when the coolant and oil temperatures are above calibrated values, the ECM then operates the secondary port throttle valves and secondary injectors based on engine RPM and throttle position. The effect is similar to when the secondaries on a 4-barrel carburetor kicked in. Now the engine is running on all 16 injectors and all 32 valves. When the secondary system is activated, a torque peak near 4,800 RPM is established. The console-mounted power switch controls the opening of the secondary port throttle valves, thus limiting engine operation to the primary inlet ports only. The ECM computes the proper air-fuel ratio for all driving conditions using a speed-density fuel calculation program. This calculation is based on inputs from the manifold pressure, intake air temperature, and throttle position sensors, as well as engine RPM, which is determined from the crankshaft sensor signal. The ultimate result of this induction system is 2 distinct valve timings and optimized air-fuel flow in a car that has both attractive low-speed and impressive high-speed characteristics.
End Part 2. You should now prepare to take the next part of the test for this course. If you are unsure of the answer, you may stop the tape to think about the question, review the course book, or rewind the tape and review it before answering. Test Part 2. Start this part of the test at line number 4. Question number 4. The LT5 cylinder block is made from A. Cast iron, B. Ceramic, C. Aluminum, or D. Steel. Question number 5. The recommended fuel octane for the LT5 is A. 87, B. 89, C. 91, or D. 92. Question number 6. The 2 secondary throttle blades on an LT5 begin to open A. when the primary valve is 80% open, B. when the power switch is on full, C. when both the coolant and oil temperatures exceed prescribed limits, or D. all of the above.
The LT5 has an ignition system comprised of 4 coils, each with 2 separate plug leads mounted at the rear end of the engine beneath the intake manifold. It is a direct fire system controlled by the ECM. Each coil fires 2 spark plugs simultaneously when only one cylinder is in its compression stroke. This is called the wasted spark method, because the second plug fires harmlessly in the cylinder that is in its exhaust stroke. A crankshaft position sensor sends a signal used by the ECM, which calculates the precise spark timing needed for the engine's immediate operational mode. The ECM then signals the proper coil to fire the spark plugs. This sensor eliminates the need for timing adjustments. Spark advance is constantly modified by the ECM to best match conditions as computed from engine speed, load as determined by manifold pressure, throttle position, and coolant temperature. The electronic spark control system minimizes knock and allows the engine to adjust to various grades of fuel, changes in altitude, temperature, and humidity. With no knock present, spark timing is optimized to maximize the engine's performance at the lowest fuel consumption and emissions levels possible. The LT5's cooling system is a unique feature of this remarkable power plant. The thermostat has been relocated from the normal outlet side of the engine to the inlet side in order to better protect the engine from the effects of thermal cycling. Thermal cycling occurs whenever cold coolant is circulated through the engine ahead of the temperature-sensing thermostat. The thermostat itself has a bypass valve which unseats according to the coolant flow rate. This valve limits the amount of erosion and high pressure damage to the radiator when the engine is running at high RPM or when the thermostat is closed during rapid acceleration. Normally, the thermostat begins to open at about 180 degrees Fahrenheit and is fully opened at 195 to 200 degrees. The cast aluminum thermostat housing incorporates two assemblies in a single unit. There's the heater inlet and outlet, and there are the engine bypass and radiator outlets to the engine inlets. Fittings on the housing are machined to help reduce leaks. The centrifugal water pump is capable of circulating nearly 100 gallons of coolant per minute at 6,000 RPM or 12 gallons per minute at the engine's low 650 RPM idle speed. A high fill bottle is mounted higher than the radiator in order to improve filling and self-purging. The pressure relief cap is on the fill bottle, not on the radiator. Two 5-blade plastic fans are controlled by the ECM. They are driven by separate 150-watt motors and work either together or separately depending on air conditioning head pressure, engine cooling temperature, and vehicle speed. An engine oil cooler is located between the AC condenser and radiator. In the event of severe oil contamination, the oil cooler must be flushed. Oil temperature is controlled by a thermostat in the oil filter housing, which begins to open at 192 degrees and is fully open at just over 200 degrees. If the oil temperature exceeds a predetermined temperature, the ECM will turn on the check gauges light to notify the driver. The ECM will also deactivate the secondary full power system, regardless of engine power switch input. The LT5's ECM has 5 additional duties to perform compared to the L98. It controls the engine power light on the console and the secondary port throttle valves. It also controls the secondary injectors, the sequential fuel injection system, and the secondary fuel pump. There are 2 O2 sensors, one per exhaust collector, that continuously monitor the air-fuel mixture. The L98 has only one O2 sensor. The speed density system is used by the ECM to determine airflow using a set of precise calculations for optimized fuel delivery and overall performance. This is in place of the mass airflow system used in the L98 through the 1990 model year. And finally, the ECM has a 7,000 RPM rev limiter which shuts off fuel delivery beyond that point to avoid accessory drive damage. 2 hydraulic engine mounts are used to improve engine isolation from the passenger compartment. And 2 2¾ dual exhausts provide low restriction while maintaining high output capabilities. 2 catalytic converters, one per pipe, are placed directly into the tubular exhaust manifolds. Midway through the 1992 model year, the exhaust manifold catalytic converter was converted into a 2-piece assembly to simplify catalytic converter replacement.
End Part 3. You should now prepare to take the next part of the test for this course. If you are unsure of the answer, you may stop the tape to think about the question, review the course book, or rewind the tape and review it before answering. Test Part 3. Start this part of the test at line number 7. Question number 7. The thermostat on an LT5 is located in the coolant stream A, at the inlet to the engine, B, at the outlet from the engine, C, at the inlet to the radiator, or D, in series with the oil cooler. Question number 8. The thermostat housing on the LT5 incorporates the A, heater core inlet, B, engine bypass, C, radiator outlets, or D, all of the above. Question number 9. The ignition system on an LT5 consists of A, 4 coils each with 2 plug leads, B, a distributor with the coil in the cap, C, a distributor with a remote coil, or D, none of the above.
Chevrolet dealer service bulletins currently list 17 different service procedures which can be performed on deficient engine components. Instructions for performing these procedures can be found in the Corvette Service Manual. The first procedure on the service bulletin list is the R&R of the throttle body and air intake duct. Start by disconnecting the negative battery cable. If the throttle body is being removed, drain the high-fill coolant bottle. This will prevent coolant from flowing into the intake ports when the throttle body is disconnected. If the throttle body extension is being replaced, transfer the intake air temperature sensor to the new extension. Be sure the retainers are in place on the screws. Remove the electrical connectors from the TPS and IAC and the hoses and fasteners from the throttle body. Then remove the throttle body. Note that the TPS is set at the factory and should not be adjusted. The second service procedure described in the service bulletin is the R&R of the intake plenum and related pipes and connectors. To remove the throttle cables from the linkage, compress the cruise servo assembly. This rotates the linkage, making the process easier. Make certain the electrical connectors are removed from the TPS and IAT sensor and that the vacuum and coolant hoses are removed. Next, open the fuel filler cap. Then remove the fuel return line from the fuel rail assembly. It is not necessary to relieve fuel system pressure in order to remove the intake plenum. If the plenum is being removed, the high fill bottle must be drained to keep coolant from pouring into the intake ports. If the plenum is being replaced, transfer the map sensor and its bracket, the throttle body extension, and the ignition module to the new unit. Remove the electrical connectors from the ignition module, the map sensor, and the remaining connectors. Cover the injector housings and intake openings. Be sure the vacuum hoses and electrical connectors are accessible before securing the plenum assembly to the injector housings. Finish the service by reconnecting all of the remaining electrical connectors, hoses, and fasteners. When servicing the direct ignition system, make certain not to ground the tachometer terminal, as damage to the DIS module or the ignition coil can result. Service to the ignition module is limited to replacement. Apply silicone grease between the face of the module and the intake plenum to aid in module cooling. When performing a compression check, first remove the INJ1 fuse in order to disable the ignition and fuel systems. Note that dwell is controlled by the DIS module and cannot be adjusted. To service the fuel rail assembly and injector housings, first open the fuel filler cap, then relieve pressure in the fuel lines by connecting a gauge. Drain the fuel into a suitable container. Disconnect the fuel lines, electrical connectors, fasteners, clamps, and hoses from the assembly, and remove the PCV grommet from the injector housing. 9 bolts hold the injector housing in place. Remove them, then remove the hose clamp. Note that the left housing incorporates the coolant, temperature sensor, and fan switch. Individual injectors are readily replaced. Be sure to select the appropriate primary or secondary style. You can tell the difference by the O-ring groove on the bottom of the secondary injector. In 1991, a change was made to the injector housings. 1990 units have 3 plugs pressed into holes machined into the bottom of the housing. When replacing a 1990 injector housing, the solid plug should face the front of the engine. When reinstalling the injector housing, be sure that the spark plug wiring harness retainer is secured by the injector housing rear bolt. The secondary port throttle valve solenoid and vacuum reservoir has 2 sources of vacuum needed for actuation. One is from the plenum, and one is from an auxiliary pump located near the right front tire. Both sources are connected to a reservoir, which in turn is connected to a solenoid that controls the actuators for the secondaries. To check for leaks in the system, isolate individual components and apply vacuum. In its non-actuated mode, the solenoid is vented to atmosphere. A slight leak in the solenoid is acceptable in the actuated mode. The electric vacuum pump overcomes this leak. Note, too, that the reservoir has a check valve that prevents the vacuum from leaking out of the solenoid. The oil filter contains a baffle that keeps oil from draining when the filter is removed from the housing. It is effective until it is turned upright. Turning the filter downward again will allow the oil to spill out. To remove the oil filter housing, begin by removing the serpentine belt. Now, remove the bolt retaining the belt tensioner to the cylinder case and remove the tensioner from the vehicle. Disconnect the oil cooler lines. To accomplish this, place a 1 1/4-inch wrench on the nut and strike the wrench with a mallet. This should loosen the nut without loosening the male adapter on the filter housing. If it is necessary to tighten the male adapter, take care not to over-tighten it, which could crack the housing. The torque specification on this adapter is 11 Newton meters plus 180 degrees. With the oil cooler lines disconnected, remove the oil pressure sensor from the housing. Then remove the bolt retaining the generator bracket and the bolts retaining the oil filter housing to the cylinder case. Within the housing are the temperature control valve assembly, the oil filter bypass valve assembly, and the cooler bypass valve. All three valves can be disassembled. When reinstalling the housing, be sure to install new O-rings to ensure leak-free engine operation. All electrical connectors and terminals should be secure and dry. If replacement is required, use the special splice kit.
End Part 4. You should now prepare to take the next part of the test for this course. If you are unsure of the answer, you may stop the tape to think about the question, review the course book, or rewind the tape and review it before answering. Test Part 4. Start this part of the test at line number 10. Question number 10. When servicing the direct ignition system on an LT5, A. Apply dielectric grease to the back of the module. B. Remove the plenum to access the module. C. Do not ground the tachometer terminal. Or D. All of the above. Question number 11. The secondary port throttle valve solenoid on an LT5, A, is pulse width modulated by the ECM. B, will leak some vacuum in its activated mode. C, controls vacuum supplied by the engine only. Or D, controls vacuum supplied by the vacuum pump only. Question number 12. Before performing a compression check on an LT5, A, remove the INJ1 fuse. B, disconnect the secondary throttle valve vacuum lines. C, release the fuel pressure. Or D, all of the above.
Service to the coolant pump, pipes, or water outlet begins with the removal of the clamps and hoses from the coolant outlets, radiator inlet, and the inlet pipe. Next, remove the coolant hose and inlet pipe assembly. Remove the bolt retaining the belt tensioner to the pump and disconnect the tensioner from the engine. Next, remove the hose clamps and the hose from the pump. Remove the bolts retaining the generator lower mounting bracket, then remove the bracket. Note the position, length, and type of bolts before removing the coolant pump. Improper installation of the bolts could result in severe coolant leaks, damage to the coolant pump housing or engine front cover, or interference with the serpentine belt pulleys. Now remove the bolts retaining the coolant pump to the engine front cover. There's no difference between the right and left side engine mounts, but the brackets are different. They are stamped RH for right hand and LH for left hand. Notice the tab in the mount bolt hole. This tab mates with the notch on the mount and should face the front of the engine. To service the accessory drive and supporting brackets, begin by using a 1/2-inch drive ratchet to retract the belt tensioner. Slip the belt rearward off the coolant pump pulley, then remove the belt. For reinstallation of the serpentine belt, refer to the belt routing illustration label affixed to the upper radiator support panel. Removal of the power steering pump, reservoir, bracket, and pulley begins with the draining of the power steering fluid by removing the lines from the reservoir and pump. Cap the lines to prevent contamination or loss of fluid. Now, disconnect the vacuum hose retainer attached to the power steering pump reservoir. Disconnect the upper coolant hose and the water outlet pipe. If you've not yet done so, disconnect the serpentine belt. Remove the breather pipe bracket and the breather pipe. Remove the plenum extension. Unfasten the top housing bolt. Disconnect the front mounting bolt. And remove the pump from the vehicle. To remove the generator, first remove the plenum, then disconnect the lower support bolts and the bracket. Remove the battery cable. Disconnect the electrical connector to the generator. Unfasten the rear support bracket bolt and remove the generator from the vehicle. If service is required on the starter motor, begin by removing the battery positive cable and the electrical connector. Remove the mounting bolts. Pull the starter toward the front of the engine and rotate it for easy removal. Removing the right side secondary linkage shield will increase access to the starter motor if necessary. Numerous sensors on the engine provide the ECM with data critical to performance. The camshaft sensor is located in the left cylinder head between number 3 and number 5 cylinders. The coolant temperature sensor, or CTS, is a thermistor mounted in the engine coolant stream. The engine oil temperature, or EOT sensor, is also a thermistor type, which is mounted on the right front of the engine below the oil filter. The NOx sensor is mounted in the lower left side of the engine block. There is a manifold absolute pressure, or MAP sensor, mounted on the intake manifold. The intake air temperature, or IAT sensor, is a thermistor mounted in the throttle body extension. 2 oxygen, or O2 sensors, are mounted in the exhaust manifolds. The throttle position sensor, TPS, is a potentiometer connected to the throttle shaft in the throttle body. The vacuum sensor for the secondary port throttle system is located under the ECM. The vehicle speed sensor, or VSS, is a pulse generator driven by a speedometer gear and is mounted on the output shaft of the transmission. Removal of the clutch fork requires removal of the complete exhaust system and transmission. See videotape 2 of this program for instructions on this procedure. To remove the housing, align the fork on the 2 flats of the release bearing and push the fork away from the bearing. A twisting motion may help. If the disc shows signs of excessive wear, the ball stud locking screw may have to be removed, and the ball stud may have to be loosened to disengage the fork and housing. To remove the clutch fork, remove the ball stud locking screw, the ball stud, and the fork and ball stud from the fork. Be sure to lubricate the ball stud and clutch fork fingers prior to reinstallation. Be certain to mark the alignment of the clutch cover and the flywheel. Then remove the clutch cover assembly to flywheel bolts evenly, one turn at a time, until spring pressure is released. Failure to release the clutch cover assembly bolts uniformly may cause damage to the assembly and/or the flywheel. When reinstalling the clutch cover assembly, make sure the reference marks on the cover and flywheel are aligned so as to retain their proper balance. Follow the proper tightening sequence. If the flywheel is being replaced, new balance weights must be installed on the new unit in the same hole locations as the old flywheel, using the flywheel to crank bolt hole pattern as a reference. Notice the hole pattern is not symmetrical and that the flywheel can be bolted to the crankshaft only one way. Make sure the flywheel is installed with the crankshaft dowel pin in the 3 o'clock position. To remove the clutch pilot bearing from the crankshaft, use the bearing removal tool. Notice the cup plug in the crankshaft. Make certain not to disturb the cup plug or serious oil leaks could occur. Alternate procedures for removing the pilot bearing, such as packing it with grease and hydraulically driving the bearing out, should not be used as they could dislodge the cup plug. Tape 2 of this video program discusses the service procedures for replacing the cup plug and pilot bearing. There are 2 secondary injector modules that plug into the harness. They are easily accessible. Each module supplies voltage to 4 secondary injectors. These modules are controlled by the ECM. If an oil leak has been detected between the camshaft cover and the head, the cover must be removed. Begin by removing all electrical connectors and fasteners. The foam insert shown here should be replaced. Before reinstalling the cover, install the end plugs and new spark plug bore O-rings. Be sure to tighten the cover bolts in the correct sequence. If a leak has been detected on the oil pan side rails, it's necessary to remove the pan. When reinstalling the assembly, install a new oil pickup O-ring. Tighten all fasteners to specification in sequence. At the time of this video's production, an engine exchange program was in effect. Requirements regarding serviceable and non-serviceable items, warranty claims, processing procedures, and shipping instructions are described in Chevrolet dealer service bulletins. The removed engine must be returned complete as it is removed from the car without examination other than as described in the service bulletin. On engines equipped with a one-piece exhaust manifold catalytic converter assembly, the engine must be tilted upward at an extreme angle. This is necessary to provide sufficient clearance for the assembly as it is raised from the vehicle. Take special care to prevent damaging the windshield or body while lifting the engine. The first step in preparing an engine for shipment is to drain and measure both the oil and coolant. Capture a sample of each liquid in the plastic vials supplied. Record the measurements on the repair order. Remove all of the plastic shipping plugs and covers from the exchange unit and install them on the removed unit. If the engine leaks, mark the leak area on the engine and on the illustration supplied with the shipping container. Write the TAN reference number on the leak identification form. Place the oil and coolant sample vials, leak detection charts, and a copy of the repair order into the shipping box and attach them to the original engine. Then repack the removed engine into the original shipping container. Be certain to fasten the engine into the container securely. Diagnosing electronic faults on the ZR-1 Corvette is accomplished the same as on a standard Corvette. However, because of the additional sensors, actuators, and switches, there are about 10 ECM fault codes specific to the LT5 engine. Always refer to the appropriate service manual for instructions on diagnosing and repairing any faulty circuits. It is critical that you follow the diagnosis tree as published in the manual.
End Part 5. You should now prepare to take the next part of the test for this course. If you are unsure of the answer, you may stop the tape to think about the question, review the course book, or rewind the tape and review it before answering. Test Part 5. Start this part of the test at line number 13. Question number 13. Failure to uniformly release the clutch cover assembly bolts from an LT5 may damage the A. Pilot bearing, B. Housing, C. Fork, or D. Flywheel. Question number 14. If the flywheel on an LT5 is being replaced, A. New balance weights must be installed in the same locations as the old flywheel. B. The replacement flywheel is precision balanced at the factory, so no further balancing is necessary. C. Test the flywheel for balance after installation. Or D. Increase weights by 1/2 ounce to account for the loss of mass due to wear. Question number 15. The vacuum sensor for the secondary port throttle system on an LT5 is located A. Next to the actuator, B. Under the ECM, C. Near the left shock tower, or D. On the plenum. The video portion of Part 1 of this course is now complete. You're ready to take the final portion of the test for this part. Be sure to continue with Part 2 of this course, LT5 Engine Mechanical. Please rewind the videotape. Good luck.